Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what do? Well, we provide mentoring and training services for different mechanical engineering codes. And we provide equipment, certification, and re-rating services as well. We'd be pleased to help you. So let's continue with our slides. Welcome back, folks, to episode 8. Yes, we're already on episode 8. We're going to look at example 3.7 from API 579-2. And this one's interesting because we're going to be looking at level 2. And particularly, we're going to be looking at a sphere. And our goal is to develop a minimum allowable temperature chart versus pressure. And that way we can sort of see the limitations so that the CET can be established. So let's continue with our studies. So we want to perform a MAT for a spherical reactor as a function of pressure, very similar to example 3.6, but it was constructed to ASME, boiler pressure vessel code, Section 8, Division 1, and it's an old vessel, 1958. And the material construction is SA204 grade A, which is an alloy material. And we'll talk a little bit more in a slide about where we would need to use that. And so the data we have is 112 megapascals, 1625. Design conditions 4482 at 150 centigrade. And 650 psig at 300 Fahrenheit. The maximum operating pressure is 2689 at 150 degrees centigrade, or 390 psig at 300 Fahrenheit. We have a reactor vessel. Let's continue. So we have the inside diameter of 2896 millimeters, or 144 inches. We have a nominal thickness of 42.9 or 1.6875, and the actual thickness is 43.6 millimeters or 1.7165 inches. We have a weld efficiency of 0.9. We continue with more detail. We have a corrosion allowance of 4 millimeters or 0.1563 inches. We have a CET, the critical exposure temperature, which is given to us by the process folks, and that's at 16 degrees centigrade or 60 Fahrenheit. And there was post-weld heat treatment performed, so perhaps we can take advantage of that. There was no impact test available, so that limits the type of a design, analysis that we can perform. We're going to take a look at what strategies to use. We have two in our toolbox: option A, governing friction and exemption curves, and we have the impact testing. So because we don't have any impact tests, our only option is to go through option A, governing thickness and exemption curves. Let's continue. Step 1.1, determine the MAT using the governing thickness and exemption rules. First of all, we use the boiler pressure vessel code, Section 8, Division 1 and 2. We confirm that from earlier. And the design is less than 172.5 megapascals. We've confirmed for SA204, we have 112 megapascals, so we're good to go with it. Now, for uncorroded governing thickness, it's based upon the nominal uncorroded thickness for a pressure vessel. So we use 42.9 millimeters or 1.6875. Formed heads, we don't have any in this application, but we would use the minimum thickness. And for pipe components, we would subtract the millitolerance, and that is not applicable. So now we continue to step 1.3, determining the material toughness. So we have a material specification. We go to table 3.2 for low alloy steel plates that are not listed in table B, C, and D. Therefore, we use curve A. That's applicable. So then we move on to the toughness curve, figure 3.4. So we know we have a curve A, we know the thickness. We move up to curve A, we go across, and at the end of the day, our mat is 93 Fahrenheit or 34 degrees centigrade. So in step 1.4, we determine the mat, and it was determined from 3.4. For flanges, we were reminded that we're supposed to set it to minus 29. And if we're thin parts, then we would set it to minus 55. But in most those cases, it's not applicable. So and for carbon steel nuts, and we set it to minus 48. Again, not applicable. Now we try to take advantage and use the future mat reduction checks to see whether we can get that, because it's not low enough yet. So we have the first check is we have a P1 group 1 or P1 group 2 material, and that's a fail because we have an ASME P3 material group 1. The wall thickness, it's has to be less than half an inch, and we've got 42.9 or 1.6875 inches. And post weld and heat treat and no subsequent work, the only one that passes is the applicable. So at the end of the day, we have to conclude that we're going to be doing a level 2. Method A, step 3, where we involve a stress ratio based on thickness. So we got a thickness ratio, we've got a stress ratio, and we've got a temperature pressure ratio. And in this case, we're going to be using the stress analysis. So we're going to calculate the membrane stress for a cylinder as a function of internal pressure. And we're going to use Appendix A for the 2007 or the Annex 2C for the 2016. The previous example, we're going to have to calculate a couple key items, including the corrected inside radius. We check this, we take half the inside diameter plus the future corrosion allowance plus the corrosion that we've already used up. We do a calculation, we get 72.1563 or 1832 millimeters. So then we continue, we determine the corrected thickness, and then we get 1.765 minus 1.563, you get 1.560 or 39.6. We've determined our corrected thickness and our corrected radius. We're ready to perform some calculations, just like the previous example, and we do some tests to make sure that the equations that we're going to use are applicable, and this is for thick and thin membrane theory. And so here's our check. So we've got a pass there, and we've got a pass there. So therefore, we can use this equation to do our analysis, which is the pressure times the radius over 2 times the stress and the joint factor minus 0.2 times the pressure. Continue here. So we have an Annex A and an Annex 2C. And we've got our circumferential stresses. We've determined that we can continue to use this equation. So now we know our geometry, our radius, and our critical thicknesses that we calculated earlier. We can come up with a relationship, and we determine that the stress times the joint efficiency is equal to 22.065 P. Now it's very simple to go ahead and develop a table. Table 3.7, we've got to figure out which curve to use. And because of the age of the vessel is 1958, we're pretty much stuck using the Note 2 design, which is shown there, and we're going to be using the 0.4 curve, but the rest of the curve is the same. Determining is step 4, the stress ratio, and looking at the limitations. So there's a very handy equation. So we take our mat that we determined in our first stages, we subtract our TR, and we take the maximum of that. So if we fall below 0.4 on the stress ratio, then we've got to go ahead and we've got to use 104 degrees centigrade or minus 155 Fahrenheit. At the end of the day, we've determined our curves. We used our pressure, we used our stress ratios, and we found out our temperature reductions shown here. And as soon as we hit 0.4, then we had to use 155 minus 155 as our value. And that concludes our work. Quite a few conclusions here to make. So the level 2 assessment, good news, we pass the operating conditions. But there's a few things to keep in mind. Remember that the CET, the critical temperature, must be greater than the MAT, and so for the corresponding pressure. So remember, we just did a pressure curve. So we know that our CET is 16 degrees centigrade. And so our reactor is at 390 psig or 2688 kPa. And if we, according to this table, if we use that pressure of 390, then we can reduce our mat reduce our mat equal to 9 degrees centigrade. So we're okay. So if we look at our graph, you can see 390 degrees. And we're sitting here at 44 Fahrenheit, or approximately, and you make that adjustment, and we're fine. So that concludes this topic. I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.